And welcome. Today we're going to talk about simply and multiply connected domains. Okay, so what we're going to really be talking about is, properties of sets D, and of course these are always going to be open sets. That's what we're principally interested in. And the properties of open sets we'll be looking at are really topological. And so we'll get a better idea of what these topological ideas are, but they're essentially ideas about sets. And we'll have some big picture things to talk about in a little bit. So okay, these are open sets we're going to talk about, and we're talking about properties of sets that are these open sets. So the first definition we have is that of a D, an open set, is simply connected and I'm going to call that SC from now on if every simple closed contour in D only encloses points in D. Okay, so all right, let's talk about what it's usually best just to draw a picture. All right, so think of this as some set in the complex plane. We'll call that D. All right, so what we have to do is take a contour. I say a contour is just some contour like that, right? And I want to see if any contour that I can lay inside of this set, will it enclose only points that are themselves in D. So of course, if I can draw a circle like that, that'll be a closed contour, and of course it's containing only points inside of D. So check. And can I do that for every closed contour I pick? And for this drawing that I put down here, the answer is yes. In this particular case, D is what we call simply connected. All right. All right. So let's talk about another example then. We'll just do an artwork example. I'm going to have like a set like this, let's say. Right. And this will be my set D. I'm going to kind of put just a shading around the outside here to say everything else that's shaded is not in D. Like that. All right, now D is actually going to have some holes in it. So of course, if I draw it now, I want to test this set out. I want to see, is this set simply connected? And of course, the idea is that I have to be able to find a contour. If I put a contour there, and clearly it's enclosing points that are only in D, so that's okay. But if I go over here and I draw this contour, like that, now I'm actually enclosing one of the holes, right? So I'm going to call those right there. I'm going to point those out. Those are holes. Okay, and these holes, of course, now because I can find a contour that encloses points that are not in D, so what we say is no, this set D is not simply connected. Okay. All right. So so kind of what's the moral of the story here? Simply connected means no holes. Okay, so the only other thing we need to establish again is the sets D that we're considering, of course, are open. And when I say D is a domain, what I'm saying is this is an open set. And what is an open set again? Let's just an open set is, of course, that if for all points Z that are elements of D, I can draw. There's some sort of neighborhood around that point I can draw, or that's entirely a subset of D. So if I pick a point inside of D, I can draw a little tiny neighborhood around it. It could be very, very small, but as long as I can enclose it by that. And what we really mean here, open, that just means that every point every point, all points are interior. And all this does for us, at least practically speaking, is that we're able to we don't have to worry about points on a boundary. Okay. All right. So now that we have those definitions kind of put away, now we can talk about some example sets. All right. So where is this all heading? You might ask. Why do we need this definition? Of course. Now, so far in this class on complex variables, we've been studying. We study functions f of z, and especially we're looking at domains of analyticity. So we'll say that f is, I call it A, analytic, on a set D, right? And so this set, of course, is our domain. So let's talk about a few sets. Okay, and really what we want to study then are these domains defined by the analyticity of f, right? So this is what we're studying. Okay, all right, so and that's where these domains come from, is really from these functions f of z. All right, so let's talk about a function f of z is equal to z squared. Okay, so of course it's analytic entire. So what we say is d is equal to the entire complex plane. And of course, C is simply connected. I can take the whole plane. No matter what contour I can put any contour anywhere. It's going to enclose points in the complex plane. So that's trivially true. All right. So now let's try another example. Maybe a little bit more interesting. Let's try the function f of z is equal to the principal log of z. All right, so if I draw, and of course this log then, of course we're going to have the principal branch, so we're going to say that theta is less than or is greater than negative pi and less than pi, right? So I can draw what d looks like. So d, of course, is equal to the complex plane minus all points z such that the real part of z is less than or equal to 0. Okay? All right. So we usually draw that by kind of just scratching off the negative real axis like that. Okay. So d is everything else all around here. Okay, and so that just keeps going off, right? So that's our branch cut. All right. So is d simply connected? Well, we can try to think about this. Now, if I draw a circle over here, certainly that encloses only points in d. And of course, again, I can now do something like this, draw a curve like that, a contour like that, and my contour gets drawn like that, and of course it's enclosing points only in D. All right, so those two examples look like it works. Are there any contours I can draw that lie entirely inside D that enclose points that are not in D? And the answer is no. And now the principle, the only way we could do it, so the points that are not in D are, of course, this axis here. But if I draw a contour around, let's say if I draw, I'm going to do that over again. I'm going to draw a big loop that goes around like that. All right, in order to enclose these points, I have to actually connect that curve like that. But the contour must cross the cut, the branch cut, right? Which is not allowed. Because, of course, our contour C must be entirely inside of D. All right, and so because it actually contains a point that's not in D, contours like this are not allowed. So this is not valid. And what we say is D in this particular case is simply connected. All right. All right, so now let's go to another example really quick. All right, let's talk about the domain of analyticity of 1 over z. Okay, so we want to know what the domain of that is. Now we know this function is analytic, but it's analytic on the complex plane minus the 0 point. There's one point where it's not analytic, So we can draw that like that, and I'll usually just put like a little hard dot right there. All right. So if I draw a curve out here, that looks good. I can draw that around, and of course that's enclosing points that are entirely in the domain. But of course, if I draw a contour that goes around the origin, I am enclosing a point that's not in the domain of analyticity. And so what I say is D is not simply connected in this case. Okay. All right, so of course isolated points, if they're deleted from the plane, that immediately is essentially, even though it's not a large hole, it's sort of more of a pinprick. And that's just metaphorical. The idea is that there's, and so that is essentially a hole in D. Okay, so that's the way we like to think of this. And hopefully this gets you an idea of what's going on. So now what we're going to do is we're going to talk about why is this, why is this useful? So maybe I'll go back to this page here. Oops. Let's go back to this page here, and now just say, let's discuss, so why is this important? Okay, and we have to go back to our previous video on the Cauchy-Goursat theorem. Okay, so the Cauchy-Goursat theorem says if f is analytic on a contour, I should say a simple closed contour, C, and all interior points, so the idea is here I have some simply closed contour, and I've done like that. And of course f is A, and I put that in quotes, throughout all of this, and on the contour itself, then we know that the contour integral is equal to 0. So now, so what we can do is extend this idea of what we'll call the CG theorem, which is that if D is domain of analyticity, and D is simply connected, then every simple closed contour, SCC, in D has the property that if I take the integral around that contour, dz at 0. So that means whatever, so for instance log, okay, so let's go to an example here. So let's look at what I mean by this. That means that if I take log, principal value of log, all right, and we know its domain is the everything in the complex plane except for the negative real line, all right? So log of z, f of z. And if I have a contour that lies entirely in D, I know then that log of z, so this is a simple closed contour, right? So I'm talking about a contour like this. dz has to be integrate to 0. All right, because of course this closed contour lies entirely within the domain, and it doesn't and it doesn't enclose any points that are not. And of course this is a very important result, and so that's a really nice fact to know. And of course, we'll get to more of why this is meaningful a little bit later, but we're just building some of this theory. But hopefully we can start to see how a lot of this is connecting. Okay, so the next thing we want to do is talk about, okay, what if your domain that you're interested in is not SC, if it's not simply connected. Okay, so let's see if we have a name for that. We're going to call it a, this type of domain, we're going to call it multiply connected domain. Okay, and I'll call that MCD. That'll be my abbreviation for that. Okay. So again, so let's see what we can do about these sort of sets. So for instance, then, if I go to my f of z is equal to 1 over z, the domain of analyticity is, of course, going to be the complex plane minus the 0 point. Okay, so that's the domain, and we can draw that like this. Okay, so we're going to call that a multiply connected domain. So now we're going to talk about contours. We're going to talk about a way to handle domains like this in reference to contour integrals around closed contours. So I'm going to state a theorem. And the theorem is it's an adaptation of the Cauchy-Goursat theorem. Okay, I'll put that as a parenthetical. And I'm going to say, suppose that A and B hold, and I'm going to define what A and B are right now. A is C. There's some contour C, which is a simple closed contour, and we're going to make it counterclockwise. So I'm going to draw it like here. That's what I'm going to call C, and it's going around like that. All right, and then I'm going to say, now I'm going to say that there are a series of contours. We'll call them CK, for K is equal to 1, 2, 3, all the way up to some finite number, N. Okay, and they are all inside. Okay, and these are also simple closed contours, and they're all inside of C, and none overlap or contain each other. All right, and so what we're talking about, and the next thing they do is that they are clockwise oriented. So we're talking about now, so the outer contour is counterclockwise oriented, and now we have a series of inner orientations here. So of course we have something like that. So we have a clockwise oriented, and we have a series of this. So we're going to call that one C1, and then there's another one here. Okay, so right now I've just defined a few things, and now I want to see, what can we take away from this? I'll call that C2, and of course I can make more of these, right? But I'll just take 2 for this particular example. And then what we find is, all right, so what we find is then, given these are our definitions, A and B, we have these things like this, then if a function f of z is analytic in D, which I'm going to call the region inside C but outside of C1 and C2, if is analytic in D, which is going to be inside C, outside of all ck. But then we're also going to include the boundaries. We're actually going to include the actual contours themselves as well. Then we have the following property. Integral over c of f of z dz plus the sum over the integral over all of these subcontours, if you will, k equals 1 all the way to n of f of z dz, that's equal to 0. Okay, so we don't want to give a really deep proof to this theorem, but the idea here is that what we're going to do is we're going to make this, if f is analytic all throughout here, what we're going to do is just sort of put a bridging contour in there, and I'm going to have it go around like that. I'm going to do another bridging contour. It's going to go around like that. And then I'm going to bring these contours back and go in the opposite direction. Go through like that. And you see that on these parts right there and there, because I'm going this way and then I'm going back, and I'm going this way and going back, they cancel out and they don't actually create any net value in terms of the total integral. And because it's analytic, and this is so once I have that, I'll call this C total is going to be equal to C plus the sum CK, okay? Because of that, I can write it down. So this is a simple closed contour that's analytic on the domain of F. We can simply break up this contour into these subcomponents, and we can invoke Cauchy-Goursat to say that it's 0. So if you want to go explore that further, it's a pretty straightforward proof. It would take me a few more lines, but it's not that big of a deal. Okay, so let's talk about what's the meaning of that. The meaning is, of course, that so let's go to an example. Let's go back to our f of z, okay, as equal to 1 over z. So we know that its domain of analyticity is the plane deleted with the origin deleted. Okay, so let's say I have some big contour, and it's a pretty strange and weird contour, right? I'm going to call that CW for weird, okay? So W means weird. All right, so clearly on this domain enclosed by C weird, it contains the origin, and the origin is trouble, okay? Well, now what I'm going to do is I'm going to make another contour inside, and it's going to be just a unit circle. So I'm going to call C N, N for nice. Okay, it's nice because it's simple, right? I can parameterize it easily, right? So using the theorem, right? So actually Cn, if I make that negative Cn, it becomes a clockwise, right? And first of all, everywhere in this domain, including the boundary itself, f is analytic on the domain outside Cn, okay? And inside Cw, of course, kind of trivially so, right? And because of that, I can write down the theorem Cw integral fz dz plus negative Cn fz dz has to be equal to 0, which then implies that Cw, which is the weird contour, is equal to Cn, because of course I can make this a positive orientation and make that a negative there, right? And that's the way it always works. If I go in the opposite direction, and the integral just becomes negative, and then I can move it over to the other side, f of z dz. All right, and so what this does is say that we have, as long as we have analyticity, T allows deformability of contours in the plane, right? So as long as we're in our analytic domain, I can deform a weird contour into a nice contour that I can then explicitly compute the integral on. All right, so that's a really nice result. So let's just talk about the example. So integral C weird, f of z. I don't know how to parameterize this contour. It's a pretty ugly one. But I know I can but I know for C nice, I can write that as z of t is equal to e to the I t, and I can go from negative pi all the way to pi, in which case I can go, and then I can write it as, so we're talking about 1 over z here, so that becomes integral from negative pi to pi of e to the negative I t, right, because this is 1 over, and that makes it a negative exponent, times, then I have to put my z prime, so z prime is equal to I e to the I t, which I e to the I t dt, which becomes integral from negative pi to pi of I dt, because those cancel, okay, in which case I get 2 pi I. So every closed contour that encloses the origin, no matter how wild and strange, and how varied its pathways are, it can be deformed to a very simple contour, which I can explicitly compute, and they're all equal to 2 pi I. All right, so that's a really nice example. And now we have sort of an indicator. The idea that this independence of path is the same thing as a deformability of contours. This is a really nice result, and we're going to use it a great deal to compute integrations in the complex plane. Thanks very much.